So this is just the picture that you saw, except it's in 3 dimensions. And this is a time series, and for this, you have time, and you're alternating between the two lobes over there. Now, as I said, it does not, the Lorentz model does not represent convection, not past r equal 1.01 or something like that. So people, because Lorentz model is important, people have searched for an actual physical realization of it. And here is a water wheel made by Willem Malkus. And this, the motion of this is actually described by the Lorentz model. This is not convection anymore. This is water pouring down. These are a bunch of paper cups, or cups, let's just say, that leak. And you pour water, and you can imagine that when there's disequilibrium between, you're going to spin because you're heavier here, and you keep pouring down. But which direction are you going to spin in? It could be that once you get going in one, obviously you could spin in either direction. There's nothing clockwise or intrinsically clockwise or counterclockwise to this water wheel. And it could be that once you get going in the counterclockwise direction, you're always going in the counterclockwise direction. But it turns out that this water wheel behaves like the Lorentz model. You get into a regime where it's going around and then less fast and then switches direction. And they often have these in museums, these things. Okay, so this, kind of is the opposite of the usual procedure where, usually you have some physical situation and you make an equation that describes it here. They have these equations, and then they looked for a physical system that would obey that equation, and this water wheel does. And now we come back to convection, and for convection, okay, let me take a little break and see how our system is doing. How's it? It's still there. It's okay. I believe it's not going to go credit. I think it's actually just going to get here to the center and just stay there. I think. Though it's taking its time, as it should, because this is very close to where it's unstable. It's just barely unstable, and being barely unstable means it's going very slowly, either growing very slowly or decreasing very slowly. So it's decreasing very slowly there. Anyway, so going back to this, let's not do full screen since it takes a while. Yes, okay, so we were talking about convection. Yeah, let me go back to where I was doing this. One of the approximations we made in our long trek through convection was, we did free slip, we did this, but we went to the two-dimensional case. We assumed independence in the y direction. We assumed a system of straight rolls. And then forever after, we just did these little cross sections here where we did this. We didn't think about that direction at all. And that is one of the many things, approximations that we made, that becomes invalid very quickly. Here, this is now, there was a series of investigations by Busa, very, very famous person who was also interested in geophysics. He's done an amazing amount of work. It's amazing to learn that he's still alive, still producing. He is just an amazing guy. He has been around since Chandrasekhar's time and is still, okay, so what is this picture here? This alpha is what we called Q. This is the Prandtl number axis, and this is the Rayleigh number axis. And what is this? This is called the Busa balloon, which again people have made jokes at. He's a very good-humored guy, but he is very round. Germanic guy, likes to eat, likes to drink. So the Busa balloon, people imagine and made jokes about this. He makes jokes himself. This is a surface in three-dimensional space of when the straight rolls are unstable. They are unstable to when this describes their width roll. Is it like this or is it like this? And this is the Prandtl number and the Rayleigh number. And they become unstable to various things called cross roll, zigzag, a whole zoology of it. And let me show you some of them. The skew varicose instability has a bunch of straight rolls becoming unstable to a perturbation that grows, shrinks, that where the wavelength is bigger, smaller, like that's skew varicose. You can see here a contraction and an expansion of the wavelength. Everybody see that? So this is this becoming unstable to a perturbation like that. And this is a subcritical instability, meaning that you end up in a whole nother place when you undergo this instability. Generally, that's what we said before, it's subcritical, you don't know where you're going. you're going, because the place where something like this is just the basic state plus a little bit of the unstable eigenvector. Something here, you're going, you don't know where. Anyway, so this, you can see this does not look like a saturated version of this. The cross-roll instability is when straight rolls become unstable to rolls that are perpendicular. And that's the cross-roll instability. And here's another funny sociological fact. These pictures, do these look like convection? Well, you might think, what do I know about what convection pictures look like? I'll tell you they don't. What these pictures are of is sand. This is a vibrated granular layer. This is a shaken layer of sand. And so why am I showing you this as an example of convection patterns? And there are two reasons for that. One is that when Busse was doing all this work, which was in the 1970s, there was not the web and all this stuff, and you didn't have such good photographs in journals, and the journal articles, if you look at them now, the photos are really hard to see, and you certainly didn't have stuff on the web. There was no web, there was nothing. So it is hard to find visual examples, and it then kind of fell out of fashion because you've done everything in it. So that was Busse. But then in the early 2000s, or actually late 1990s, other people were doing other experiments, say with these granular layers and shaking them, and they found the same kind of instabilities that Busse had found for convection. Sand, convection, shaken sand, heated fluid layer. Why should they be similar? And the answer here is that these principles of dynamical systems and of symmetry and so on are universal. They're what I'd like to call, I hope I'm not offending anybody here, math. That's just what patterns do. And it doesn't matter if it's sand or if it's rubber or if it's water or anything. And they do the same thing because they obey continuum equations, and these are symmetry properties. Okay, so that's that. Here are some other pictures. I told you the whole rest was pictures, so you don't have to worry. Let's check on our simulation. I think it's just going to sit there. This is what turned out, this was now very interesting, and this was in the year 2000. There's an article in Nature, very prestigious. It said that actually it's not just that you have Busse balloon, that you're unstable, that your straight rolls are unstable to other patterns. They're unstable, that they actually get kinks and this and that. Actually, right at threshold, you don't get straight rolls. You get this spiral defect chaos. And why didn't anybody ever notice before? Well, because they didn't do experiments that were big enough. If you have a very, you have to have by big, what you mean is the ratio of the horizontal lengths to the depth. And it turns out that almost immediately what you get in many fluids is something that looks like that. And here all this time people have been studying straight rolls and the instability of straight rolls to some wiggles or something, but that's really not what you got either. So that was a big discovery, you can imagine. But by then, convection patterns were a little bit played out. Again, if you want to study math and pattern formation, convection is pretty much unparalleled, great system. And if you want to study instabilities in spheres, this is simulation and prediction by Paul Matthews of what happens in spheres, where you have spherical symmetry, you break the spherical symmetry, and you get these patterns. This is my own work. Here. I'm running over. How long do I? Okay, I want to run over just a tiny bit because I do want to finish this. Okay, of course, convection is a practical matter as well. In geophysics, we have, of course, the mantle of the Earth. It's a very, very slow-moving, but still geological scales are very, very long. That's what's happening in the Earth. Is all this in the mantle of the Earth? You have this lava, or I don't know if it's lava. Somebody who knows more about geophysics can tell me. Anyway, stuff that is moving at some speeds, and that's convection that's happening down there. And of course, in the ocean, you have convection in the atmosphere. Convection is not just a mathy subject to study pattern formation. It is what controls, the air, the water, the Earth, everything. And now, let me get to something. Just the last tiny mathy thing, and this I really do want to get to. You remember we talked yesterday about certain bifurcations. We talked about a bifurcation that was capable of making a limit cycle that was not a Hopf bifurcation, a saddle node bifurcation on a limit cycle, right? And we said that there were steady states here, and then they ceased to be steady states, and you had a limit cycle. And you remember I said that the way you knew it was because they were at the onset, the period was very, very, very long because it remembered it had been in a stable state and now it stopped having a stable, steady state. Okay, so in convection, This was my very first project after my PhD. This is convection in a cylindrical geometry. It's axisymmetric, and this is a slice. You can see through the axisymmetric, hot and cold, and you have these convection rolls. And in time, what's happening is the rolls are moving out, and you have the formation of a new little one at the center, and they're annihilated as they as it gets to the end. And if you look at the period, if you plot a time series of what's happening, you see that its period is extremely variable. Here it's kind of regular, but here you see it's spending all of its time here, or all of its time here. And if you plot the temperature at two different places in a two-dimensional representation, you get exactly what we were talking about there yesterday in this completely theoretical way, where you had a stable point here and an unstable point, and then you had limit cycles. So that is exactly what you see, and yet it is a completely physical situation. You have you have this limit cycle here, and you see it here, you're oscillating. But as you get close to the bifurcation, it is very slow, because there is a stable point that is approaching. There's a collision between a stable and unstable convective state here. And that is forming, that is an actual physical realization of the saddle node on periodic orbit that has, where the period goes to infinity as you get to the threshold here. Here, this is a picture taken over here where it's just the rolls are going in some regular manner. And here, the rolls are basically just hanging out here, and then all of a sudden, one disappears, a new one starts, and then it hangs out, hangs out, hangs out, hangs out, and then all of a sudden that happens again. That's what these things are. So these bifurcations that you learned about in these completely theoretical, schematic way yesterday are actually realized in systems like this, in actual physical convective systems. And there I stop. Thank you. Well, let's look at our picture. There. Iggy's staying here.